happy to introduce Alex Guterman, and he will tell us about the version of Frobenius theorem on matrix maps and beyond.
Thank you very much. It's a pleasure to speak here on this nice conference. And, it's always nice to be in Yaffo. It doesn't matter if it's pilgrimage or as a scientist. So I will speak about Frobenius theorem and some our results around it, but everything goes back to the following question by Dedekind. He asked, assume we have a certain finite group, say of order n, and we consider the multiplication table of that group. In fact, we consider variables, commuting variables with relations coming from that table. This is a certain matrix, and working in free algebra, we could find determinant of this matrix. Well, determinant will be some homogeneous polynomial of degree equal to the order of this group. And as usual for polynomials, we would like to decompose them into the product of irreducible factors. How this decomposition looks like? Well, in abelian case, this question was answered by Dedekind in full generality. So he proved that if our finite group here is also abelian, then the group determinant, so the determinant of the Kelly table could be decomposed into the product of linear factors. So let me just show you this on the example. Assume we have a cyclic group of order 3. We denote its elements by commuting variables, and we have this multiplication table. And when we compute, I permuted the rows here just to avoid minuses at the end, but you could always permute it back, no problem. So you could compute the determinant of this matrix, what is called group determinant. This will be the following polynomial of degree 3. And then this decomposition found by Dedekind looks as follows, where epsilon is a certain root of unity. So you could figure out this decomposition in many different ways. But one of the good ways is to realize that it is related with another important table coming from that finite group, namely the character table. So we consider this group, its reducible representations, and characters, traces of matrices, of images. And you evaluate these characters over conjugacy classes. And it is visible that each row from the character table here is in bijective correspondence with factors, with coefficients in that factors. So, and this is a general phenomenon in commutative case, also discovered by Dedekind. When he tried to see what happens for non-abelian So he was thinking everything is possible to decompose up to the product of linear factors in those times. In those times, it was not the Frobenius theorem about non-existence of certain extensions of reals was not proved yet. So Dedekind was looking for nice hyper-complex number field where he put everything, where he could decompose everything to the linear factors. So he was going in the wrong direction and was asking around what to do. And after some, even for small groups, if you consider evaluation over complex numbers, like quaternions, permutations, or for the free, you already have nonlinear factors if you decompose over complex numbers. So Dedekind was asking around, and after some 16 years, it was Frobenius who established the complete answer. So for any finite group, the decomposition is as follows. A group determinant could be decomposed into the product of irreducibles, of irreducible polynomials, but the general phenomenon is as follows. The multiplicity with which each factor appears here is nothing but the degree of this polynomial. So this is a general rule for such decomposition. And even there is certain relation with characters. Actually, this was the same paper. The previous result was proved in the same paper where Frobenius created the representation theory of finite groups. So, in the also he was asking about the following uniqueness question. Assume we have two irreducible representations. They are in correspondence with irreducible polynomials, actually, of a group determinant. So assume our irreducible representations, assume they are equivalent. The question is, do they correspond to the same irreducible factor here or not? To answer it in positive, it was necessary for Frobenius to prove the following result in the same paper. So he was reducing everything to some canonical forms where everything was, where some invariants were possible to compute, and it was necessary to see what are the maps which allows you to reduce things while preserving determinant. So he was trying to solve the following question. Assume we have a certain map on matrices of fixed size. We assume this is linear and bijective map. And coefficients are complex. What can be said about the structure of maps such that determinant of a matrix, of any matrix, is equal to the determinant of its image? Of course, we all know such maps. Say transposition is one of possibilities. This is the linear map, bijective preserving determinant. Similarity is also of that form. Even if you consider such a generalized similarity, namely pre and post multiplying of your matrix by two invertible matrices with a product equal to 1, it will still preserve the determinant. And the deep result of Frobenius is to show that there are no more transformations of this type. So necessity is evident here. These maps will preserve determinant, but the deep result is sufficiency. There are no more maps preserving determinant. So nothing but these two types and possibly their composition. And of course, say transposition could be expressed in that form. You could ask your students about it. But so you really need two types. So this was another theory coming from that paper by Frobenius. Later on, this result was generalized by Schur. He was considering minors, subdeterminants of a fixed order, and he was considering maps preserving these minors of fixed order, and proved that they are standard in a certain way. We will not go into the details here about minors, but we'll mention another result, which is due to Guterman. It is about zero locus of determinant. So we assume that the map singular matrices to singular matrices, possibly to different singular matrices, but it should be singular anyway. Again, linearity and bijectivity, and this is notation for singular matrices. And so to say, standard result appears. Of course, there is no this restriction that determinant of the product is equal to 1, which is natural. And actually, the result of Frobenius and Schur was proved by matricial technique, and this was quite involved proofs. Guterman used projective geometry. So he was considering maximal singular subspaces. Of course, singular matrices, they do not form a subspace, but you consider still subspaces with singular elements, and their structure is open problem actually. But he was considering dimensions of maximal singular subspaces. This was inducing some bijection between the complements, which were lines. So he was using main results from projective geometry, so to say, fundamental theorem of projective geometry, and was able to obtain the same standard form over any fields. So later on, it was Wilkin who suggested different method to work with such maps. It was based on his characterization of maximal subgroups of classical groups. Using his Wilkin diagrams, he was able to characterize those maximal subgroups, and then illustrated the applications of his characterization in that paper by considering this problem, by reproving, say, Frobenius result. So the idea is as follows. You're considering bijective map on matrices of size n. So all of them are here. And of course, you have these naive examples about which you could always guess. And these naive examples, so to say, standard maps for different invariant with a different maps sometimes. And the set you are looking for is this. So if you fix certain property S or certain condition S, then those maps which preserve it, they are in this tower. That's the idea. And then using some linear algebra technique, it is possible to prove that corresponding subgroup is maximal. So there is no possibility, and as a result of its characterization, the outcome is there are not so many maximal subgroups in classical groups. So you know that your subgroup is should be maximal, but if you prove separately that it is not coinciding with standard cases, so it must coincide with a set of naive examples you have from experiments. So this how this theory works, but certainly over characteristic zero, algebraically closed field. Well, you may ask why it is interesting to consider such maps. Of course, not only as illustration for other theories exist, but usually when you consider different invariants, it's important to see what are the structure preserving maps, what are the maps which preserve these invariants to understand this better the situation. For example, here we all know that determinant could be computed by Gaussian elimination, and this could be done in polynomial time. And actually, the fact that Gaussian elimination exists is actually based on the result of Frobenius I just mentioned. The result of Frobenius is telling you there are considerably many maps which allow you to evaluate your matrix and simultaneously preserve determinant. So by this set of maps, you could reduce your matrix to a certain manageable form and then compute. This is about determinant. And if you look to similar invariant called permanent, the situation, I mean, it looks even easier, but the situation is much more, is considerably different because it is still an open problem if there exists a polynomial algorithm to compute permanent. And in general, people believe that there is no such algorithm, because if there will be such an algorithm, then you could solve travel salesman problem polynomially, and you will have many other nice consequences. But nobody knows the answer. And to understand why it is so, so to understand why you need, well, of course, by definition, you need factorial number of operations, but the Reiser formula tells you that actually you should use exponential number of operations. And Reiser formula is something very easy. You could consider you could consider row sums of your matrix, and you could multiply all these row sums. Assume you have a certain matrix, and you want to compute its permanent. This will be very much similar with products of row sums, except here you might have repetitions when you multiply all elements in the brackets. But in permanent, everything is parameterized by bijections, so there are no repetitions. But inclusion-exclusion principle allows you to remove repetitions, and that is why how Reiser formula is working. but the reason why it is still exponential time to compute permanent by Reiser formula, and why it is so difficult is could be easily explained by Marcus and May result from 60s. They actually shown that the set of maps which preserve permanent is rather small. So you could either pre or post multiply by permutational matrices. You have diagonal scaling and translation, and that is all. So what you can do with permutation of rows and columns, there is no good canonical form you could reduce to via these maps. So it's very seldom when permanent is preserved, and that is why it is so complex. Well, there are many other applications. For example, in central simple algebras, you consider norms, nothing but the determinant of left regular representation, and it turns out that there was a question: does the norm determine the central simple algebra up to automorphism? And the answer is positive, and it is based actually on Frobenius result. Another question about group determinants. So, yes. Yeah, I mean, positive means isomorphic and anti-isomorphic in this context, certainly. Yes. So same question, same isomorphism question, but on the group theory level. We have seen this group determinant, and the question is: assume we have. Is it possible that two non-isomorphic finite groups have the same group determinant? And it was the result by Formanek and Sibley. They in fact show that group determinant determines the group up to group automorphism. So, and again, the proof was based on Dieudonné result on singularity preservers. So in general, there are many problems of that type, and everything, of course, depends on the coefficient ring, on the map, on the assumptions, on the invariant itself, and you could ask the same questions for relations between elements, for subsets, or for invariants. And sometimes the answer is standard, and sometimes it is far from being standard. For example, if you look to the following problem, you are looking to those maps which preserve roots of certain polynomials, multivariable polynomials. What is their structure? Sometimes you have rather standard answers. For example, for these matrices of finite order, so matricial polynomials, and the answer is standard. But, and for example, for idempotence, even less maps. But let's look at the following result of Porta about nilpotence. Then you have considerably many maps. Some extra summons here. And sometimes these maps are uncontrollable, but in some cases, they are standard. I will not go into the details, just I would like to show that, again, if you have several variables, sometimes maps are standard, like zero products. And when you consider commutators, here when it is either image is a certain commuting subspace or your map has the following standard form. So the following characterization exists. I will not go into details about general situation with multivariable polynomials. There are different methods which people apply in these studies. But let me pass to the following question. Well, we all know that that matrices over non-commutative structures are important. So what will happen with such with analog of Frobenius result over in non-commutative situation? So for example, in division ring generality. Well, here we have an interesting result by this and Mehta. They actually proved that the existence of determinant, whatever it means, you know, if your determinant is if you are dealing with determinant of certain non-commutative object, then it immediately leads to many problems. For example, it will depend on basis. If you change the basis, you could still consider this, and sometimes your determinant is multiplicative, but you couldn't cancel here. It's this is, but this cancellation will require you to replace these things, and it's impossible. So, well, non-commutative determinants, they live their own life, but this result tells you that if you have this functional with certain natural properties to be satisfied, when your ring is automatically commuting. Well, there are many ways to get around. Of course, one could think about determinant in two ways, at least. One way is polynomial representation. So your determinant is good polynomial, you could always evaluate it, or you could attempt to evaluate it. And another approach is to see, to look at the determinant as a homomorphism. Nice homomorphism. So it was Guterman who considered the second approach and constructed the notion called Guterman determinant, actually useful in K-theory when you compute K1 functors, for example, the splitting homomorphism. But the major idea is very easy. So you need for determinant, determinant needs some commutativity to live in, to be say a good homomorphism. So the natural way to obtain something commutative from vision ring is to take the quotient by commutant, and this will be the minimal commuting object by some group theory result. And then you naturally add 0, and it turns out that the following function exists and unique. And this is Guterman determinant. So again, some natural assumptions about row-column linearity. If you add multiple of one row, then you don't change determinant. If you multiply the row, then you change determinant in that form, and so on. So Guterman proved that such a function exists. Well, and in that context, over non-commutative structures, it is of course natural to ask in the generality of semi-linear maps. So you allow your map to act on this product in the following way, where sigma is a certain automorphism. And the natural question will be what happens with Frobenius result. So this is an answer. So for division algebra over a certain commutative field, which is sufficiently big, and any semi-linear map over K, which preserve the determinant. Well, in finite dimensional case, that's all. In infinite dimensional case, it is necessary to assume surjectivity in addition. Then, again, you have a certain standard form for semi-linear maps preserving Dirac determinant. So it is either that form or the following form is translation. And again, it is these two forms are unique to scalar factor. Let me just show you briefly how it works. For example, it turns out that this condition that your map preserve determinant, the determinant of image is always equal to determinant of A is sufficiently strong. For example, you could download automatically that the map is invertible. Why? Just look at the kernel of T. If you look at the kernel of T and you assume on contradiction that it contains some non-zero element, that means that let's compute the determinant of this matrix. Determinant of A is equal to determinant of T of A. But this is element of the kernel, so it's determinant of 0, which is 0. So this line shows us that there are no elements of maximal rank, and whatever, well, you have some explanation of this rank, in the kernel. But you could always do the following. There are no other non-trivial elements as well, because if you could always take a matrix of complementary rank, so your element from the kernel has some rank, say k, less than n. Then you could always take B such that rank of B is n minus a, and rank of a sum is equal to the size, and then compute determinant of B. From one side, it is 0, right? Because of the rank. But from the other side, this is determinant of T of V. Let me add 0 here. And by 0, I could always mean determinant of T of A. T of B plus T of A, because A is from the kernel. But when T is linear and determinant is preserved, so I could always say that this is determinant of A plus B, which is non-zero. So you have a contradiction. So this is just a few lines to show how how trivial things could be proved, to give you a little bit flavor of what is going on. But behind the general result, there is a reduction to the coherence preservers. So for Dieudonné determinant preservers, it is possible to show that they are, it is possible to provide a reduction to coherence preservers. So coherence is important relation with, in Minkowski geometry and special relativity. So two events are coherent if the distance is equal to time multiplied by the speed of light. You could interpret it geometrically. You could reinterpret it algebraically using this Hermitian matrices here. So nice invariant. And Lacan-Huang characterized coherence preservers. So basically, we are reducing Dieudonné determinant preservers to that result. This is over division rings. It is possible to proceed further on. For example, you could deal with local rings where all non-invertible elements form an ideal. So this ideal is nothing but Jacobson radical, and the quotient is division ring again. So you could have nice model theory over local rings. They have IBM property, they are projective free, and that is why there is a good notion of rank. It is defined correctly because rank is just image, the size of image of a free direct summand. And again, I will probably skip the details, but will show the analog of Dieudonné result. So in case we are over integral local domain, which is finitely generated as a K module over certain commutative ring K, then again the characterization of singularity preservers is given here, and this maps out certain standard form, and the way these results are proved is different. So for all this, we need to characterize. We deal with maps which preserve something. To achieve some structural results for such maps, we always need to characterize these properties we are dealing with in terms, in some numerical terms. So you could just compute, you could just compare cardinalities and things like this. So here we are dealing with the following pencil. So for a couple of matrices, we consider those lambdas such that this thing is singular. And when I say singular, I mean it has some non-trivial kernel. And it turns out that this set of scalars is very useful because it measures rank 1 property. So it could be shown that if my matrix has rank greater than 1, then I could always find, when I always have such a structure of this set. It is rather technical to show this, but finally it is possible even to obtain such a characterization. My matrix is of rank at most 1. If for any matrix B, this set, again, it is written here. The set of scalars is either the whole ground field K, ground commutative ring K, or it has the following restriction on cardinality. So this is a nice numerical characterization of rank 1 property, which is actually rather technical to prove. Afterwards, it allows you to deal with singularity preservers in that generality. Let me just finish with some recent result, also related to those maps preserving singularity. I mean, Jedone result about maps preserving singular matrices. We have seen already them, but there is another interesting notion which is called a total graph. So when you consider a certain algebra, you could always construct many different possibly infinite graphs. Like you consider matrices, and you could construct commutativity graph, or you consider average algebra.
The viewers cannot see that area.
Okay, yes. So, sorry.
The black pen is better.
Double mistakes sometimes improve the situation, but not always. Especially in teaching, in giving lectures, yes. So you could consider commutativity relation. And when you put in your graph, your vertex set is nothing but the set of whole matrices, and you put an H if your matrices commute, and if they don't commute, you don't put H. Well, it's better to remove, not to have a lot of garbage here on this graph. It's better to remove center scalar matrices, of course, commute with everything. So let's remove them first, and then put H when you have commutativity relation. So this is very nice infinite graph, and its structure, for example, its diameter and other parameters were quite important for many problems. And sometimes you really have nice results. For example, diameter of matrices of a complex number is equal of this graph constructed from matrices of complex numbers. Try to guess what is the answer. The answer is quite surprising. It is 4. So for any two matrices, you could always find 3 guys in between, such that one commutes with another, and these two matrices, they not necessary. So such things. So this is maximal distance. But well, there are many problems of this type for commutativity graphs, which are nice infinite graphs. For say zero divisors graph. Again, and here we deal with singularity. So we say that what is called total graph is a graph such that again vertices they are just matrices, and we write an H if the sum is singular. So it is an open problem. It was an open problem to find automorphisms, the set of automorphisms for the total graph. So well, people were considering this problem, and some results are available. For example, these results from some paper of linear multilinear algebra with heavy machinery to prove even 2 by 2 case. So for us, we decided to look at this problem as preserver problem, as a problem of about linear maps preserving some invariants. And it turned out that this was successful approach. So, well, in general, people believe certain standard solution, certain standard characterization for such maps, but this was shown only for 2 by 2 matrices with few other examples, and we realized we could apply the following approach. So there is a nice result by Taliner and Schemel about, well, another generalization of Frobenius result. So instead of preserving determinant and assuming linearity, we could consider this pencil condition, which somehow unifies linearity and preserving determinant preserver condition. And then obtain the structure, and as a consequence, show that these maps are linear. So such a nice nonlinear, generally nonlinear result. So it was Konstantin Kostara who considered even more general problem. We have 2 maps here, T1 and T2, and assuming that at least one of these maps is continuous and surjective, he was able to prove when if this pencil preserving condition is satisfied, then again we have T1 equals T2, and the map is linear and standard. Well, this was result using a lot of complex analysis, assuming continuity and so on. So we were able, with Artem Maksayev and Valentin Promeslov, we were able to show that by algebraic approach, which was valid for any algebraically closed field without any continuity assumption. And again, there is a standard result. And on the base of this result, later on, together, maybe this will be probably the last thing I'm going to mention today. So together with Konstantin, Artem and Valentin, we were able to obtain the complete characterization for automorphisms of a total graph. So here the technique is not linearly algebraic, but we really working with action of the map T on the cliques of non-singular matrices and compute how large is the image, consider different numerical invariants, how they are performed, and finally we were able to characterize, to solve in positive this question about automorphisms of total graph. Yeah, so thank you. I will stop here.
Questions?
I have a very basic question. So, getting back to the Guterman determinant. Suppose that your D is a central simple algebra, is a central division algebra.
Yeah, any division.
You prefer it to be finite dimensional base center.
I see.
Then this n by rate of n by matrices over that D is a central simple F algebra, where F is the center of D.
Yeah.
and it's equipped with a reduced norm form. What's the connection between this reduced norm form and the geometric determinant?
The thing is, this reduced norm form will be quite different, right? Because the net determinant is a rational function. But this thing, if I am not mistaken, will be will have certain polynomial expression in general. Yes. So this will, the net determinant is nice for homomorphism, but the price you pay for it, but it has no good representation. When you want to compute it, it becomes ugly rational expressions, and when the size grows, it's quite heavy. So I don't see any direct relation, but it could be that you have certain denominator of all rational fractions, and you multiply with it, and it could be somehow related. But I mean, just by definition, these are quite different objects. But who knows?
There is a condition. If you compose the determinant for the reduced norm, you obtain the reduced norm of
so that common denominator is just nothing but lifting. I see. Yes. Okay. Yes, it could be over central simple algebra. Yeah.
More questions? We should say that we can get questions from the online viewers too. Comments. Say. Okay, I'm telling you, any online watcher that you can that they can make questions too. Comments.
Which auditorium is bigger? This one or online or remote auditorium?
This one. Okay, there are no more questions, then those thank you.
Yeah, that's fine, but it's called for the